Good morning, everyone.
Good morning.
Good morning.
Morning.
All right, we're going to wait just one more minute. Let me get that link for all everywhere into chat, though. Give me 1 second. Wait for it to connect. Cool. There y'all are. All right, I see that's 11 o'clock. A couple people coming in the last second. So there's the link one more time, and I'm going to activate the quiz. I'm going to try this from my phone. So maybe this will do it. Lock. All right. Let's see. Trying out new technology. Yeah, so you should see the daily quiz up for today. So I want you to use implicit differentiation to find the derivative with respect to y for the equation 2x squared plus y squared equals 2x. 2x squared plus y squared equal 2x. I'll write it out on the whiteboard. So we get it for the recording. I'll give you all until about 11:04. So I know we're missing a couple people and some are coming in. There's the link one more time. All right. We got everyone here now. Like I said, 11:04. So we got just under 2 minutes. All right, we got 1 minute left. I'm liking the answers that I'm seeing coming through right now. I've got 1104. 27 responses, looks good. So I'm going to lock answers here in 5, 3, 2, 1. Locking answers now. All right, so looks like most of y'all are getting the correct answer. So let's just go through it real quick. Again, the idea here is we're taking the derivative with respect to x of both sides of the equation. And whenever I'm not taking the derivative with respect to x, I got to make sure I apply the chain rule, because we're always just assuming that that variable has some relationship to what we're taking the derivative of. So take the derivative with respect to x of both sides of my equation. I have 2x squared plus y squared is equal to the derivative with respect to x of x. And from there, I just kind of focus on either side, right? Where do I see maybe the easier derivatives for me to do? Where are those appearing? Just go ahead and do those, right? So on that right-hand side, I see the derivative with respect to x of x. So what is that?
And just one.
Yeah, it's just 1.
1.
Yeah, thank you. Yep, so on that right-hand side, I'm just gonna have a nice good old 1. And then the more interesting stuff is kind of happening on the left-hand side. And maybe you're feeling really comfortable with that sum or difference rule with derivatives. But again, just for good practice, I like to write it out in that the derivative of 2x squared plus y squared is the same thing as the derivative of 2x squared plus the derivative of y squared. And I can separate derivatives over sums. And then again, I look at those derivatives I still have to calculate and say, okay, well, which is probably the easier one of the two? Well, we're used to x's. We're taking the derivative with respect to x. So I take the derivative of 2x squared, which bring the exponent down, multiply by it, and subtract 1 from it. So I get a 4x for the derivative of 2x squared. And now the interesting part. I got to remember how to take the derivative with respect to x of y squared. Well, I just take the derivative of the outer function multiplied by the derivative of the inner function, i.e. the chain rule. So I kind of act like I'm taking the derivative with respect to y, bring the exponent down front, subtract 1 from it, rewrite what I had inside, which was just a y. But then I need to make sure I multiply by the derivative of the inside. And since I'm taking the derivative with respect to y, it's my unknown, it's what I'm trying to find. So that's why we write that dy over dx. That's what we talked about on Wednesday last week, and you kind of saw a good bit of in the homework. But now all the calculus is done. I'll get you here in a second, Desante. All the calculus is done. Now I just need to do my algebra, right? Solve for dy over dx. So move everything that doesn't have a dy dx over to the right-hand side. So I'll subtract a 4x from both sides. And then divide what I'm multiplying the dy dx by, which is a 2y. So the answer in this case, from that equation, 2x squared plus y squared plus x, how y changes with respect to x is this 1 minus 4x all divided by 2y. Again, that idea that how y changes with respect to x depends both on what your x value is and your y value is. So Desante, do you still have a question? Because I know I saw you do the hand raise reaction.
Yeah, I had a question. So we know what we're solving for is going to be on the bottom then. So like dy over dx we're searching for, wait, hold on. How do I always know which one I'm searching for, like which variable for the dy over dx notation?
I'm a little confused. So we know we're searching for how y changes with respect to x. It's given in the problem, right? And when I look at my equation, it's what variables do I have?
The x and y, of course.
Yeah. So that's where I see the y appear is where I'm going to see my dy dx appear once I take the derivative. And that's going to, and as we see, that's where it shows up. And then once it shows up, I solve for it.
Okay.
Any other questions? All right, give me a thumbs up if you're good. That's that. We got a lot of people with cameras on today. Thank you. Even if it's just 4, that's a lot of people. Cool, I see a thumbs up. All right, so we're going to get on to the application of this implicit differentiation called related rates problems. And I just want to talk about it real quick before we start solving the questions, because again, you should have watched the videos before coming to class today. Okay, related rates problems, we always assume that we're taking the derivative with respect to time. So we're always assuming whatever our equation is that we have, it's going to be changing over time. If I want to talk about change over time, that's my derivative with respect to time. So we're always going to take the derivative with respect to time, just assuming t stands for time, of both sides of our equation. Okay, so when we're talking about related rates problems, this is going to be always kind of the first step after you identify what your equation is. So you're going to take the derivative with respect to time of both sides, and then after that, there's some small little mini steps, but overall, it's just plug in available information. And solve for the desired variable or rate. Okay. So I'm just always going to be identifying what my equation is, kind of variables, etc. Take the derivative with respect to time of both sides. So then I get 2 equations. Right? I'm going to get how these things are related and then how their rates are related, i.e. related rate section. Once I have both of those, I plug in the information that I need. Sometimes I'm going to have to use the first equation to find specific information, or the second equation, my related rates equation, but then I just solve for the rate or variable that I'm looking for. Okay, but the key is we're always going to be taking the derivative with respect to time of both sides, which means I'm going to have to use that implicit differentiation for all of my variables. I'm going to have to use implicit differentiation for all of my variables, which means I have to use chain rule. My variable is in time. I got to make sure I multiply by the derivative of that variable with respect to time. So go back to poll everywhere for me. You have a new equation. I don't have my nice little fancy setup today, so I'm going to write it out on Zoom as well for the recording. But what we're doing is we're considering the explicit equation or implicit equation x squared plus y squared equals 13. So it's another circle problem, right? And I again want to find how y changes over time when I know some pieces of information. So I want to find dy over dt when I know how x changes over time is equal to 2. I'm also given that x, the value of x itself, is -2. And the last piece of information is y is positive. And again, I'll give you that how to start all of these off. Take the derivative with respect to time of both sides. Squared plus y squared, and the derivative with respect to time of 13. So take it from there, do your best, and remember, or you're going to see, I'm not going to say remember, you're going to see that once you find your related rates equation, so that dx, you're going to have dx over dt, dy over dt, and x and the y variable in there. One of the things that you're going to need to figure out is what is your value of y. So use the equation that you're given to find y, and then plug all that stuff into your related rates. So I'm going to give you all 5 minutes, so 11:18, just about. Okay, work on this. Your answer should be a numeric value. It will end up being a number. Let me ask this. Do y'all want to go to breakout rooms for this one? Give me a thumbs up if you want to go to breakout rooms so you can talk to each other. All right. Got 2 thumbs up, 3. I didn't get enough. We'll do that later for another problem. 4. Do on your own. Justice, please give it at least a good attempt. You can take the derivative with respect to time of both sides. I know you can do that. All right, 2 more minutes, y'all, but I've already seen a couple answers come through and they're looking good. I saw 1 guess, and like I've always said, I'm happy with guesses. So thank you for at least responding. I want y'all to be working. I want you to be trying, all right? Cool. All right, got just under a minute, so 50 seconds. Get your answers in. Oops, let me get back to see. There's right click. All right, again, make sure you at least give me your best guess. We've watched the videos before this. You've seen some of this. I don't think the videos had a problem specifically like this, but it's the same style. You see, once you do enough of these problems, they all have the same setup and solving method. You've got to establish what your equations are. All right, I got 11:18. So I'm going to lock answers here in 5, 3, 2, 1. Locking answers now. All right. So, as I said, first step is to find your related rates equation. So you have your main equation. It's given to us in the problem. X squared plus y squared is equal to 13. I want to find the related rates, how this equation changes over time. We do that by taking the derivative with respect to time of both sides. Now again, that right-hand side is going to be nice and simple for us. What is the derivative with respect to time of 13? Well, the derivative of any constant is always what?
0.
Yeah, derivative of any constant is always 0. It doesn't matter what variable you're taking the derivative with respect to. So on that right-hand side, I've got 0. And again, on that left-hand side, I can see that I'm taking the derivative of a sum. So I can split this up into the sum of the derivatives. It's the derivative with respect to time of x squared and the derivative with respect to time of y squared. Now the variable that we're taking the derivative with respect to, that t, I don't see here or here. So I followed that same process that we learned with different or implicit differentiation when we were taking the derivative with respect to x of something like y squared, except this x changes to a t. So if I was replacing that x with a t, I would follow the same process, act like I'm taking the derivative of y squared with respect to y. So bring the exponent down, subtract 1 from it, do the power rule, but then multiply by how y changes with respect to the variable I'm considering here. So how y changes as my time changes. So dy over dt. X would follow similarly. Derivative with respect to time of x squared acts like I'm taking the derivative with respect to x. So the derivative of x squared would be 2x, but then multiply by how x changes as time changes, dx over dt. So that means on this left-hand side of my equation, I now have 2x dx over dt plus 2y dy over dt equals 0. So this is my related rates equation. That is the first big step. I have to find my related rates equation. And then once I have that, I say, okay, what am I looking for? Well, in the problem, we're looking for dy over dt, how y changes over time. Whoops. So that's what I want to solve for in this equation. That means I want to be able to get dy over dt by itself. Okay, so I'm going to go to a new board. I'm going to give you all just like 5 seconds to finish writing this down because I see at least one person still writing. I'm going to write this equation though on the next slide. So at least it'll still be there. So, but like I said, just solve for that dy over dt. So here we go, moving on. We have that 2x dx over dt plus 2y dy over dt equals 0. To solve for dy over dt, I just do the same thing. Subtract anything that doesn't have a dy over dt, move it to the other side. So I'm going to have a 2y dy over dt is going to be equal to a new negative 2x dx over dt. And then I divide by a 2y to get it by itself, dy over dt. So then I'll have negative 2x dx over dt. All of that is being divided by 2 times my y. So this is the equation that is going to give me how y changes over time with respect to that equation that we were given at the very beginning, x squared plus y squared equals 13. And if we go back real quick, I'm going to come back to this slide so you can make sure you get this stuff written down, but back for the problem, well, what do I know? What is the information that I know? I know that how my x changes over time is 2. My dx over dt is 2. I'm considering when x is negative 2. I'm kind of given this slightly vague condition when y is positive. I'm not given the value for y, but y is positive. So let's just kind of recap that when I'm looking and write the information out when I'm looking at my related rates equation. So we know x squared plus y squared is equal to 13. We have dx over dt is equal to 2. X is equal to negative 2. And y is positive. So I notice if I plug, I can plug at least 2 of those values. Right? It's not as straightforward function evaluation like we're used to seeing for polynomials or rational functions, but this is still a type of function evaluation. I know what dx over dt is. I know what x is. What is the one value that I don't know on this right-hand side? What is the one value that I don't know yet?
Why?
Yeah, I don't know y yet. But can I find y?
I'm guessing yes.
You guess correctly. What equation will I have to use to find the value of y? All I need to do is use that initial equation that we were given, right? That tells me how my x and y's are related. I'm given the value for x, which means I could solve for the value of y. So plug the x in, and this is where that condition, it seemed kind of obscure at first, but y needs to be the positive value. So plug in x being -2. So this is -2 squared plus y squared is equal to 13. -2 squared is 4, so this is 4 plus y squared is equal to 13. And that tells me y squared is equal to 9. Now to solve y squared is equal to 9, what do I do to both sides?
Find the square root of both.
Yeah, find the square root of both sides. And anytime I take the square root, I got to make sure I take both the positive and negative, right? So this means the two potential values for y could be either +3 or -3, but which one are we going to use?
The positive.
Positive.
+3, right? Because we were told in the problem that the y has got to be the positive. So y being +3. That was the last thing we needed to solve for, but it was given to us by the initial equation. Okay? I already had the parts. I just had to take a moment, step back, look at the pieces that I had, and figure out what could I use, which of these equations could I use to figure out this last missing piece of info. But now I've got it, right? Y has got to be equal to 3. So now let me kind of clean some of this clutter up around this equation. Now we're just going to plug in. So then my change in y over time, my dy over dt, is equal to -2 times my value of x, which is -2, times how my x is changing over time, which is a +2. Just plugging in information that I've found or been given. Then in the denominator, I have a 2 times the 3. So then let's see if I can get this all here on one screen still, because I can't write too much lower than that. But in that numerator, I have a -8, or a +8, sorry, because a negative times a negative makes a positive. I have 3 2's multiplied together, which is an 8. And then I'm dividing by a 6, and 8 over 6 reduces to what?
4/3.
Divided by 3.
Yeah, both you ladies got it. Thank you. 4 divided by 3. So that is my answer, 4 divided by 3. Okay, so I'm going to give you all a second to finish writing this down, but let's recap what we did, right? We started, I'll come back to this. We were given our equation, x squared plus y squared is equal to 13. We're just given a bunch of information after that, right? What defines, and then what some other random values are. And if we want to kind of cheat the process and be the smart student, that's going to be variables that are going to show up in my related rates equation, okay? But the first step, which is what we did here, is to take that equation and take the derivative with respect to time on both sides. Right? Take the derivative with respect to time on both sides, and then I'll get down to what we see down there at the very bottom. That's my related rates equation. So from there, I have two equations now. Not only how my variables are connected, so that x squared plus y squared is equal to 13, but how their rates are connected. is 2x dx over dt plus 2y dy over dt equal to 0. It's a mouthful, but those are the two equations that we now have. Once I have those equations, which we have written here, that's what's going to allow me to solve for what I want to find. In this case, it was that dy over dt, so we just went ahead and solved for dy over dt and then tried to plug in any known values. We saw that we were missing 1. We were missing what y was, but we were able to use our original equation to figure out what y needed to be, plugged it in, and we're done. Seems like a lot, but once you do enough problems, it's just that same process and some small changes because it changes from problem to problem. Take the derivative with respect to both sides, find out what you want to solve for it, plug in all known variables that you have, and then if you need to, find values for other variables. All right, questions? And if not, give me a thumbs up like always. But please, 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 please ask questions. Okay, I'm just seeing a thumbs up. All right.
I have a question about
Yes, thank you.
Okay, so like the 2's on top. So, okay, I didn't do all of that, but
Okay.
I got the same answer. I'm pretty sure I cheated in some shape or fashion. But,
Wouldn't say cheated,
okay.
mistake. Let's be kinder. Small mistake, not cheating.
Okay, so I made a mistake somewhere, but I ended up with like the same answer. I was wondering, you could explain where you got the first two, like the top rows of 2's, please?
Oh, yeah. So I look at what I have. So I have a -2. See right there? I have my x, which we said where we care about when x is equal to -2. And then my dx over dt, which is a +2. So dx over dt, x, and then already -2 from the equation itself. So that's where we got that kind of row of 2's from.
Okay, and for the bottom, we got 3 because of y equals plus or minus 3. And the 2 came from
The equation.
the equation. Okay,
Mhm.
cool.
Yeah. No, glad I can clarify that. Thank you for asking.
Okay.
Any other questions? All right, so I don't hear anything. So if you go back to poll everywhere, you now have a new problem. You now have a new problem. Okay, so this one I'm going to read it off while you're reading it. A 15-foot ladder is leaning against a wall. If the top slides down the wall at a rate of 4 feet per second, how fast will the foot of the ladder, supposed to be foot of the ladder, be moving away from the wall when the top is 10 feet above the ground? Okay, so before y'all go off, if you feel confident with this, I know there was a video that had addressed a problem specifically like this. So if you feel comfortable, you're more than welcome to move on. But a lot of this stuff, when we're not given an explicit equation, we need to find one. Okay, so draw a picture and then see if you can figure out an equation from there. Well, we're given that we have a wall. We have a nice little wall. I'm going to draw in green. We have a ground. And then we have a ladder. Okay, that black line is my ladder. It's up against a wall. And we have obviously some type of floor. So then we're given some information. Right? We're given that the ladder is 15 feet long. And the ladder is 15 feet long. And we're given that the top is sliding down. So I'm going to see that the ladder, the top of that ladder's got to be moving down, but as we know, ladders have or should have a fixed length. So as that ladder is falling down, as the top of the ladder is coming down, the foot of the ladder is also going to be going out. Because once that ladder falls directly onto the ground, it'll be just flat onto the ground. Okay. So we're given 15-foot ladder. We're given that falls down at a rate. And that rate is going to be my cue, that this is going to be some change over time. So it falls down at 4 feet per second. Whoops. Okay, so it falls down at 4 feet per second, and then we're asked when the height of the ladder, the top of the ladder, is at 10 feet. It's the last piece of information that we're given in the problem. We're trying to figure out how quickly that base of the ladder, the foot of the ladder, is moving away from the wall. But now I got to look at this image that we see here. What shape do I see appearing in that image? You can come back to the Zoom screen real quick.
A mighty triangle.
Yeah, mighty, mighty triangle. So that's probably the cue that that's the equation that I'm going to use. Okay. So let's give ourselves some variables. Right? So we had different things to talk about. So the first thing I'm going to do is I'm going to say the distance from on the ground, so from the wall to the foot of the ladder, we're going to call it a variable. What do y'all want to call it? Because it doesn't really matter.
Wait, from the foot or what?
From the wall to the foot of the ladder, so along the floor.
Oh, the floor. Let's say that A. Why not?
A. All right. So we're going to call this distance A. And what do you want to call the height of the ladder? So where it's at on the wall.
B. Why not?
Sure. You said what again? Sorry. Whoops.
B as in boy.
B as in boy. All right. So I get a nice, good triangle. We're going to call the height of the triangle B. We're going to call the floor, the length of the triangle A. So I'm going to just kind of transpose this out of my drawing. So I'm just looking at a nice, good old triangle. And then I want to think of what is an equation that will relate each of these three sides of a triangle. It's the mighty what theorem?
Pythagorean theorem.
Yeah, Pythagorean theorem. So a squared plus b squared, because we do have a 90-degree angle here, is equal to 15 squared. So this is the equation that I'm going to use. And then once I identify my equation, what did we say the next step is to find? Well, the related rates equation. Ooh, that A looks terrible. There we go. That's better-ish. Related rates equation. And how do I find the related rates equation? And take the what of both sides.
The dy over dt.
So close. It wouldn't be the dy over dt, but you had the correct part there. I want to take the derivative with respect to time. Right, that over dt. Take the derivative with respect to time of both sides. I'm just going to go ahead and fill in 15 squared is 225. And the last thing, since we now have b, how dB over dt, how B changes over time. Well, we're given that it falls down at a rate of 4 seconds. If we're falling down, we're losing height of the ladder. So if I want to represent losing height, I make it a negative number. If I'm losing something, it's a negative. So that change in B, the change in the height over time, is equal to -4. So now this is where I'm going to let y'all continue working on it. Help y'all set it up. And you got your equations. We got the reasoning behind it. Draw a picture, figure out something. And I want you to work on it together. And since I had at least a few people want to go to breakout rooms for the last one, I'm going to throw y'all into breakout rooms for this one. I'll bring y'all back in 6 minutes. So go ahead and make sure you accept that breakout room link. Unmute yourselves, turn your video on, talk to each other, help each other out, ask questions if you get stuck. Okay, work with each other to figure this out. So make sure you join that breakout room link, please. Please, please, please join that breakout room link. Please, please, please accept that breakout room invitation. Shanice, please accept that breakout room invitation. Thank you. Awesome. So while we're in the recording, let's kind of rewrite everything. So we said we have a triangle, BA 15 feet. We know how the height changes over time, which is by a -4, the -4 feet per second. And then in the problem, we're asked to find how much we're moving away, how quickly we're moving away when the ladder is 10 feet away from the wall. The foot of the ladder is 10 feet away from the wall. So these are my two knowns, dB over dt, which is -4, how my height changes over time, and how far away the foot of the ladder is. So I set up my two equations again. A squared plus b squared equal to 225. Let me write it over here in blue. A squared plus b squared is equal to 225. I think I'm being called. All right, cool. No, y'all are all working together so far. I'm going to hop in a room here in a second. But then I have to figure out, what does that look like? The derivative with respect to time of a squared plus b squared equal to the derivative with respect to time of 225. Okay, so let's go hop in a breakout room, see how people are doing. Oops. Good morning, y'all. Sorry, y'all got shafted, and you only have 3 people in here. So most everyone at least has 4 or 5. So I want to check in, see how y'all are doing.
I'm kind of fine, and I'm also kind of lost at the same time.
Which happens with related rates. Definitely very different.
I feel like I'm getting close to the answer,
Cool.
but I'm not too sure.
Cool. Well, at least you're searching for it, right? We want to practice some. So that's awesome. I wish you were feeling more confident, but I'm glad you're trying, and you should feel a little unsure. Or no, feeling a little unsure is absolutely okay. This is what I'm trying to say. Melissa, Justice, how about y'all?
I'm good. I found my answer.
Cool.
I'm getting there.
Awesome. I want the attempts. That's what I want. That's it. All right. So keep asking each other if you get questioned, if you get stuck, ask questions. Especially since Melissa says she thinks she's got it, ask her. She might be able to help you. All right. I'll be calling y'all back here in like a minute or so. So just a heads up.
Okay.
All right. So mute myself. Everywhere. All right, closing rooms. All right.
Professor Rapp,
Yeah, what's up?
the question disappeared from me and some others.
I don't know why. Sorry about that. It's active now. Thank you for bringing that to my attention. I think someone else typed it in chat as well. Yeah, so it should be back up now if you want to take your moment to type in your answer. Sorry about that. Oh, it must have been because I was trying to use, yeah, okay. Cool, cool, cool. Getting answers in. So I'm going to give you all just a second to finish typing your answers if you want to, but come back to the Zoom screen for me. I've got it all set up. Nice little recap of all the information that we derived. Okay. So this was our setup, and we said our goal was to find our related rates equation, take the derivative with respect to both sides of the equation that was given. So if I do so, again, just kind of taking it piece by piece. So the derivative with respect to time of a squared plus the derivative with respect to time of b squared is equal to the derivative with respect to time of 225. But again, the derivative of any constant is always 0. So on that right-hand side, I'm going to get a nice good old 0. And on the left-hand side, when I'm taking the derivative with respect to a and b, I apply my chain rule, that implicit differentiation. Act like I'm taking the derivative with respect to a, gives me a 2a, but then make sure I multiply by how a changes over time.
Okay,
And
I have
with
a
that-
question.
What's up?
I see you said A equals 10. Okay, how did we know that the floor was equal to 10? What did they say in the formula, that the floor was equal to 10?
Yeah, so in the problem, they said your goal is to figure out how fast the ladder is moving away from the wall when it's 10, the foot of the ladder is 10 feet away.
Oh, so that
So
was,
that was given in the problem.
that was the foot of the ladder. Okay.
Good question. Thank you. So this right here, I'm going to put that nice little red star beside, is my related rates problem. So I can see from there I have kind of 4 unknowns, essentially, just when I'm looking at by itself, what the value of A is, how A changes over time, the value of B, and how B changes over time. And my goal is to solve for how A changes over time, right? We're trying to figure out how fast the foot of the ladder is moving away. The variable that describes the distance of the foot of the ladder from the wall is A. So I want to find that dA over dt. That's going to tell me how fast that's moving away. So if I solve for dA over dt, just to do some quick algebra, save some time because we're at the end of class. And I can simplify this as well because I'm multiplying and dividing by a 2. Oops, not 2a. So I get that how these rates are related to each other is the negative of b times how b changes over time divided by a. And I know 2 of these things already. I know that dB over dt. I know what my a is, but what is the one value that I'm missing?
Just B then?
Yeah, just b. And that is when I'm going to use my equation. Right? I want to find b. I know what a is, so I can find b from that. So let's just come down here. So I want to find b when a is 10, which means this is 10 squared plus b squared is equal to 225. Just to do some algebra again, because it's already 1 minute over.
Hi, I have a question.
What's
Aren't
up?
we supposed to solve for B? I mean, solve for A, and B is given because it says that is 10 feet above the ground.
Oh, I got my variables mixed up. Yep, absolutely correct. So yeah, but at least thankfully for me, it's a nice little change. But thank you for catching that. That's what I get for trying to rush through at the end. So we're trying to find a, so we have a squared plus 10 squared, which tells me a squared is 125. And a is plus or minus the square root, or 5 times the square root of 5. So thank you, Melissa. But which one has it got to be? Could it be the negative or the positive?
Plus, I think it has to be. Wait, no. Negative?
It has to be the positive, right? Because we're talking about distance away from the wall. It doesn't make necessarily sense, physical sense, to have a negative distance, right? Distance is always a positive value, so a has got to be the positive 5 square root of 5. And I just need to plug all of this information in. So did I mess something up rushing through? So I want to find how much it's fast it's moved away. We used a, d over dt, got the negative. All right, so plug in our information. What do we get? We get a, wait, we know a is negative. All right, so it should be is 10. That's what it is. So it's 10, negative 10 times negative 4 all over 5 times square root of 5. And this is going to be bad board work, but I'm going to come up here where I've got a little bit more room. And we'll end up simplifying to 9 over the square root of 5. If you wanted to rationalize it, you absolutely could, but I'm going to stop there because that gives you your answer. The rate at which this ladder is moving away, if you plugged it into your calculator, you get more of a good decimal approximation. But that change in A over time, how fast the foot of the ladder is moving away, is 9 over the square root of 5 feet per second.
Wouldn't it be 8 over the square root of 5?
40. Yeah, why am I? This is what I get for trying to rush through at the end because I'm panicked on time. Yep, 8. My basic arithmetic skills failed me now. No, I'm going to spin it. That's why I have y'all here. I was testing you, right? Making sure you're paying attention. It was all a part of my masterful plan. Yeah, so 8 over square root of 5. Thank you for speaking up, Chevy. All right, so definitely well over time. This is related rates. They seem like two different problems, but the overall structure is the same. Identify your equation that you need. Take the derivative with respect to time of both sides. That's when you get your related rates equation. Plug in all information that you know. Solve for what you're looking for. And if you need to find more variables, use your original equation to find that. Okay. So any questions? Because I know we're over. I know some of y'all got class
Yeah.
at noon.
Okay, when she talked about the 8, where did the 8 come from? Did that come from the -10 and the 4 and the -4?
The A was, we
No,
said
the 8 over the square root of 5.
Oh, yeah. So -10 times 4 is 40, and then I would have a divided by 5 square root of 5, and 40 divided by 5 is an 8.
Oh, okay.
Any other questions? All right, I'm going to go ahead and stop the recording in case you don't want to talk about something else other than this. And you're good to stick around and ask questions. If not, you're free to go. Thank you all for sticking with me.